Welcome to lecture number 33 of the course on nonlinear structural analysis, theory and applications. So, let us recall what we have been doing over the last few lectures. So, we started reviewing the concept of stresses, and then we looked at principal stresses, deviatory stresses, hydrostatic stress, and then octahedral shear stress, okay, and octahedral normal stress as well. And then we looked at the concept of strain at a point and studied the or reviewed the concept of generalized Hooke's law. Okay. So, now we want to answer the question, what happens when you have a body which is subjected to multi-axial state of stress, okay, and you continue loading it, at some point the material will start yielding, right. So, what are the conditions based on which we can tell that the material will yield? Okay. So, that is the topic for discussion today. Okay. So, we will talk about the maximum shear stress theory in this lecture, and in the next lecture we will talk about another theory. Okay. So, let us get started. So, as I said, what happens in a general state of stress, a material is stressed to the point where it no longer behave linear elastically. Okay. So, as you recall from our previous lectures when we started discussing uniaxial stress strain relationship, okay, we have seen that a material yields when the stress, uniaxial stress, exceeds the initial yield strength sigma y0. So, that is lecture 15. Okay. So, hereafter instead of using sigma y0, I will use sigma capital Y in moving forward, okay, just for the sake of convenience. Okay. So, for example, consider a thin cylinder, right. So, thin cylinder means the thickness of the cylinder is much smaller than the radius. So, radius is, let us say, from here to here, okay, and we are not distinguishing between inner and outer radius because the thickness is very small. So, this cylinder is subjected to internal pressure P, as you can see, and also some axial force. Now, this could be axial tension, could be axial compression, okay, that we shall see, right. So, let us say this is the problem. Okay. Now, if you take an element, okay, on this cylinder, something like this, and if you use the cylindrical coordinate system r, theta and z, then we can take that element and draw something like this. Okay. We have normal stress sigma z in the z direction, which is this, okay, and we have sigma theta in the circumferential direction, which is also called the hoop stress, and then we have in the r direction sigma r. Now, for thin cylinder, it can be shown that sigma r is negligibly small. Okay. So, as you can see, this is primarily case of biaxial state of stress, because sigma r is approximately equal to 0. Okay. So, you have two normal stresses sigma z and sigma theta, and then our out of plane stresses are all 0. So, therefore, it is a case of plane stress, and these are my principal stresses because the shear stresses are 0. Okay. So, the question is, under what conditions the cylinder will yield if I keep on increasing the internal pressure or if I keep on increasing the axial force. Okay. I can also decrease it, right. How does it yield or when does it yield? So, note that you can easily determine the circumferential or the hoop stress sigma theta is equal to P r by T. We will do an example in the next lecture, there I will derive this equation, and as I said, radial stress sigma r is negligibly small. Okay. So, there are two empirical equations that have been proposed, and those equations are reasonably simple to use and well supported by experimental data. I will also show you some data. Okay. For isotropic materials, isotropic means the properties are same in all directions. Okay. So, for isotropic material, the general considerations are the following. First is, the criteria are based on magnitude of principal stresses. The principal axis or the principal planes do not play any role, their directions do not play any role, because the properties are the same in all directions as the material is isotropic. Okay. So, therefore, the criteria are based on the magnitude of principal stresses. This is number 1. Number 2 is hydrostatic state of stress does not affect yielding, and this is very much true for metal plasticity, for metals. Okay. So, recall from the previous lecture, mean stress or hydrostatic stress is basically 1/3 sigma 1 plus sigma 2 plus sigma 3, or 1/3 of the first invariant of the stress tensor. Okay. So, these two criteria are based not on the absolute magnitude of principal stresses, but rather on the magnitude of the difference between the principal stresses. And I will show you, when you base it on the difference between the principal stresses, this hydrostatic stress is automatically ruled out. It does not affect yielding. Okay, we will see that. So, the first theory or the first criterion is called the maximum shear stress theory. Okay. So, this is based on experimental observation, where researchers have seen that a ductile material yields as a result of slip or shear along crystalline planes. Okay. So, this was originally proposed in 1773 by C. A. Coulomb, but often this criterion is referred to as the Tresca yield criterion because of his contribution. Okay. What is the criterion? The criterion is very simple. It states that yielding occurs whenever the maximum shear stress reaches the value it has when yielding occurs in the uniaxial tensile test. So, I shall explain what is meant by that, but before we get into the explanation or the mathematical part of it, okay, we need to know how can we calculate the maximum shear stress for a general 3D state of stress. For 2D problem, I am sure all of you have done Mohr circle and you can determine the maximum shear stress very easily, right. But for a 3D problem, let us say this is my x, y and z axis, okay, and I am looking at the state of stress at a point in a body, right. Now, let us say you have determined the principal stresses and principal axis by solving the eigenvalue problem, which we have discussed previously. And let us say this is your principal axis 1 and this is sigma 1, this is 2 sigma 2, this is 3 and this is sigma 3. Okay. So, this element shows the orientation of the principal axis and the principal stresses sigma 1, sigma 2 and sigma 3, right. Now, if I look at this element in this direction, right. So, then what do I get? I get a 2D element, right. So, that means I can show, if I look at it this way, I can draw a 2D element which is subjected to sigma 1 and sigma 3, right, and the out of plane stress sigma 2 is shown like that, it is pointing towards us. Okay. Similarly, if I see this from this direction, okay, then I get an element where I have sigma 2 and sigma 3 axis. Similarly, if I look at it from this direction, from the 3 axis, then I get another element where it is subjected to sigma 1, sigma 2 and the out of plane stress is sigma 3. Okay. So, now each one of this I can treat as a 2D, that means I can draw a Mohr circle for that. Okay. So, I have sigma 1 and sigma 3. Let me draw a Mohr circle. So, this is my sigma axis, this is the tau axis, and for shear stress what I typically use the convention, when the shear stress tend to rotate the element clockwise, then I plot the shear stress upward, and when it tends to rotate the element counterclockwise, I plot the shear stress downward. Okay. But here that is not necessary. So, let us say on this plane I have sigma 1, on this plane I have sigma 3. For making this plot, I am assuming sigma 1 is greater than sigma 2 is greater than sigma 3 is greater than 0, all are positive, okay, in this order. So, let us say this point is my sigma 1, okay, and this point is my sigma 3. So, the center of the Mohr circle is here, okay, and you draw this Mohr circle. This is the Mohr circle for 1, 3 plane. Okay. Similarly, for this case you can draw a Mohr circle for 2 and 3. So, this is sigma 3 as I have indicated here, and sigma 2 is in between 1 and 3, and let us say this is sigma 2 as indicated here, right. Then I get this Mohr circle, okay. This is for 2, 3 plane, this plane. Similarly, for this one I get this is my sigma 1, this is sigma 2, okay, I get this Mohr circle, right. Now, as you recall from before, at a point you can pass infinitely many planes, right. So, how do I locate the state of stress on any plane passing through that point? Okay. It can be shown that the state of stress will lie either on the circle, this circle or this circle or that circle, or the space in between or bounded by this 3 circle which is shaded by yellow. Okay. So, that is what I am showing. If I take an oblique plane like this, the state of stress on that plane will lie anywhere in this shaded yellow or on any one of the 3 circles, right. Now, what was the question? The question is, what is the maximum shear stress? Okay. So, if I consider this circle, then this is the maximum shear stress. Okay. If I consider this circle, then this is the maximum shear stress. On the other hand, if I consider the bigger circle, then this is the maximum. Now, considering all 3, this is the maximum shear stress. Okay. That is what we wanted to determine, right. So, that means mathematically if I write, as you can see, tau max in this case is sigma 1 minus sigma 3 by 2 is the radius of the bigger circle. Okay. So, mathematically I can write maximum shear stress is equal to maximum of sigma 1 minus sigma 2 by 2, of course, the absolute value, sigma 2 minus sigma 3 by 2 or sigma 3 minus sigma 1 by 2, whichever is maximum. Okay. In other words, this entire thing I can write is my maximum principal stress minus the minimum principal stress divided by 2. Okay. So, now I know how to calculate the maximum shear stress. Okay. So, now let us go back to the Tresca criterion, okay, or the maximum shear stress criterion, and let us read it again. It says that yielding occurs whenever the maximum shear stress, that means tau max, reaches the value it has when yielding occurs in the uniaxial tensile test. That means, when tau max reaches a value, what is that value? Value of tau max under uniaxial tensile test. Then we say that the material will start to yield. Okay. So, let us do that. So, in uniaxial tensile test, when the material is yielding, I have, let us say, uniaxial, the axis is 1. Okay. That means, sigma 1 is sigma y, the yield strength of the material, sigma 2 and sigma 3 are 0. If that is the case, then my sigma max is sigma 1, sigma minimum is 0. So, that means, tau max is sigma 1 by 2, okay, and under uniaxial test sigma 1 is sigma y. So, sigma 1 by 2 is sigma y by 2. So, what is the maximum shear stress? Sigma y by 2. Okay. So, this is the Tresca yield criterion or the maximum shear stress theory. Okay. Now, let us understand this for a biaxial problem or biaxial state of stress or simply plane stress. So, let us say we are talking about plane 1, 2. So, sigma 3 is 0, right. There are 2 possible cases. One is sigma 1 and sigma 2 are of the same sign. That means, I can draw a stress block like this. So, this is sigma 1, okay, and this is sigma 2, both are of the same sign. That means, both are tensile here or both could be compressive, right. This is one case. Okay. What is the other case? Sigma 1 and sigma 2 are opposite sign. That means, it is like this, sigma 1, okay, and this is sigma 2. So, sigma 1 is tensile, sigma 2 is compressive. So, these are the 2 possibilities that I can think of when the maximum shear stress theory is applied to plane stress problems. Okay. So, now for each case, let us draw the Mohr circle and determine the maximum shear stress. So, first let us consider the case 1 where sigma 1 and sigma 2 are of the same sign. I am showing both tensile, but both could be compressive. Okay. So, what is sigma 3? Remember, sigma 3 is 0. We are talking about plane stress. Okay. So, if I draw the Mohr circle, so this bigger circle, this point is this point is sigma 1 as I have shown here, this is the origin, sigma 3 is equal to 0. Okay. So, I get this bigger Mohr circle, and for sigma 2 and this I get this Mohr circle, and then this is the other one considering sigma 1 and sigma 2. So, what is the maximum shear stress? Well, it is obvious, tau max is equal to sigma 1 by 2, that is the maximum shear stress. So, according to this criteria, there is no yielding if tau max is less than sigma y by 2, because under uniaxial tension test we have determined tau max is equal to sigma y by 2 means yielding according to this criterion, right. So, if tau max is less than sigma y by 2, there is no yielding. If tau max is equal to sigma y by 2, then you get yielding, right. So, that means for this case when the signs are the same, okay. So, that means what do I get? I get, if I take sigma 1 to be greater than sigma 2, it could be the other way also. So, I am saying if I take sigma 1 is greater than sigma 2, the absolute value, then sigma 1 must be less than equal to sigma y, isn't it? Because what is the maximum shear stress? Sigma 1 by 2. So, sigma 1 by 2 must be less than equal to sigma y by 2. Okay. So, that means sigma 1 is less than equal to sigma y. Why I am using this? Because like I am showing positive here, it could be negative also, both compressive, isn't it? So, this is one condition. Now, imagine that sigma 1 is smaller than sigma 2, right. So, sigma 2 is greater than sigma 1, then sigma 2 absolute value is less than equal to sigma y. So, these are the two possibilities, right. So, if I combine the two together, I can rewrite, or I am writing it again, absolute value of sigma 1 less than equal to sigma y, absolute value of sigma 2 less than equal to sigma y. These are the two equations that I obtained, and for impending yielding, sigma 1 absolute is equal to sigma y and sigma 2 absolute is equal to sigma y. Okay. Now, what is the other case? Sigma 1 and sigma 2 are of opposite sign. Okay. That means, let us say this is tensile, that is compressive, or vice versa. Okay. So, now I draw the Mohr circle. So, sigma 1 is this point, and sigma 2 being compressive, it is on the left side of this tau axis. Okay. So, now I get, this is one Mohr circle, this is the green is the other one and blue is the other one, and of course, this is my maximum shear stress. So, what is the value? Sigma 1 minus sigma 2. Now, sigma 2 being negative, this will become sigma 1 plus the value of sigma 2 divided by 2. Okay. And I am taking absolute because like I said, this could be negative, that could be positive, isn't it? So, this is my maximum shear stress, and this maximum shear stress must be less than equal to sigma y by 2. Why sigma y by 2? Because that is what we determined under uniaxial tensile test. Okay. So, I can rewrite this equation simply, absolute value of sigma 1 minus sigma 2 must be less than equal to sigma y, right. So, we have got three equations, right. This two here, sigma 1, sigma 2 each less than equal to sigma y, and this equation, this equation. Okay. So, for impending yield, I will remove the less than. So, sigma 1 is plus minus sigma y because I have removed that absolute sign. Okay. Similarly, sigma 2 is plus minus sigma y, and sigma 1 minus sigma 2 is plus minus sigma y, right. Geometrically, what do we see from this, or what is represented by this set of equations? So, let us see that. So, this is my sigma 1 axis, this is my sigma 2 axis, sigma 3 is 0. So, if I draw this line, sigma 1 is equal to sigma y, what do I get? I get this straight line. If I draw sigma 1 is minus sigma y, then I get this straight line. Similarly, sigma 2 is plus sigma y is this line, minus sigma y is that line, and then sigma 1 minus sigma 2 is equal to sigma y is this line, and minus sigma y is this line, right. And remember, this equal sign are for impending yielding, right. So, that means the region which is bounded by this, the hexagon, is basically giving me the yield criterion, or this is the geometric representation of the maximum shear stress theory or the Tresca yield criterion. What it means that when we are within the hexagon, when the state of stress is anywhere within the hexagon, then the material is elastic. Okay. If we are on the hexagon, anywhere on the hexagon, then it means the material begins to yield or continues to yield. Okay. In state of stress cannot lie outside the hexagon according to this criteria. Okay. Now, let us explain this further, but before we get there, let us answer this question, because we stated earlier that hydrostatic state of stress does not affect yielding. Okay. So, the question is, does hydrostatic stress affect yielding? Let us answer that. So, let us say I take a point and the state of stress at that point is given by principal stresses sigma 1, sigma 2, sigma 3, and I am also assuming that they are arranged in this manner, sigma 1 is greater than sigma 2 is greater than sigma 3, and they are all positive. Okay. So, what is the maximum shear stress? Of course, sigma 1 minus sigma 3 by 2, because sigma 2 is the intermediate principal stress. Okay. Now, if I change the state of stress and increase the hydrostatic stress by, let us say, P, that means I am changing the state of stress so that the hydrostatic state of stress is increased by a value of P. So, what I will do? I will add P to each one of this. So, this is sigma 1 plus P, sigma 2 plus P, sigma 3 plus P, right. Now, what is the maximum shear stress? The maximum shear stress is still this minus that. So, tau max does not change. So, if tau max does not change, that means according to the Tresca yield criteria, the hydrostatic stress does not affect the yielding. Okay. So, that is what we stated earlier. Okay. Now, let me explain this further using a simple problem of thin cylinder that you have seen at the beginning of this lecture. Okay. So, once more we take an element here, and this is my z axis, which I am calling, let us say this is principal axis 1. Okay. This is theta axis, which I am saying this is my principal axis, this one principal axis 2. So, this is sigma theta, okay, which is sigma 2, sigma z is my sigma 1, and remember sigma r is almost equal to 0 for thin walled cylinder. Okay. Now, I have internal pressure and this is subjected to some tensile force which gives rise to sigma z. Now, remember we typically arrange sigma 1 greater than sigma 2 greater than sigma 3. Okay. Now, when I talk about this geometric representation, this is no longer considered. Okay. So, this is not there. I have got 3 principal stresses and they are sigma 1, sigma 2, sigma 3. Any one of them could be larger. That's it. Okay. So, let us say initially I am doing an experiment where this pressure P inside the cylinder is small, okay, and sigma z, that means I am applying some axial tension, sigma z is large. Okay. Recall sigma r is 0. That means what is my maximum principal stress is sigma z, which is sigma max is equal to sigma 1 is equal to sigma z, right, and sigma minimum is equal to 0. So, if I keep on increasing the axial tension, eventually tau max, which is sigma max minus sigma min by 2 is sigma 1 by 2, will reach sigma y by 2, and then it will start to yield. That means sigma 1 is equal to sigma y will be indicating yield, and where we are on this hexagon. So, on this hexagon which we have seen in the previous slide, we are at point A. Okay. That means, I have increased tensile load and the cylinder started to yield. We are at point A. Okay. Now, let us do one thing. Let us keep on increasing P. So, what happens if I increase P? If I increase P, my sigma 2 or sigma theta will increase, right. But does my tau max change? No, tau max does not change until sigma 2, which is equal to sigma theta, becomes equal to sigma z, because this is my intermediate principal stress. So, let me write it, sigma 1 is greater than sigma 2 is greater than sigma 3, which is equal to 0, right. So, this remains intermediate and the tau max is governed by this 2. So, there is no change. So, if I keep on increasing the internal pressure, yielding continues and we move along this path A to B. At point B, what happens? sigma 1 and sigma 2 are identical, that means sigma theta is equal to sigma z is equal to sigma y, that is at point B, right. Okay. Now, what happens? Let us say I am holding P constant, the internal pressure is held constant, okay, such that sigma theta is equal to sigma 2 is equal to my sigma y, that means we are at this point. Okay. Now, what I am doing? I am reducing the tensile load, I am unloading in the axial direction. Okay. So, my sigma 1 is equal to sigma z, this stress will keep on reducing and eventually will become 0. Okay. But what happens to yielding? The cylinder will continue to yield because my sigma 2 is greater than sigma 1 is greater than sigma 3 is equal to 0. So, my shear stress, maximum shear stress is governed by this and that, sigma 1 being the intermediate principal stress. So, that means I am moving along this path, right, from B to C. At point C, what happens? At point C, the cylinder has no axial force, it has only internal pressure and it is yielding. Okay. Now, what happens if I reverse the direction of axial force? I was initially pulling, then unloaded it, now I am compressing the cylinder. Okay. We are not concerned about any buckling. Okay. So, buckling is not there for this discussion, right. So, what happens if I apply compressive force? So, that means this will now become negative. So, if this becomes negative, so that means sigma 2 now is greater than sigma 3, which is equal to 0, is greater than sigma 1, which is negative. This is sigma 1 is less than 0, right. So, what is my maximum shear stress? Is governed by this 2. So, sigma 2 minus sigma 1 by 2, right. So, then what has to happen? For this to remain constant, okay, because earlier whatever we have done, we had sigma 2, here we had 0. Now, here we have a number which is negative becomes positive. So, this has to reduce, otherwise tau max will never remain constant at sigma y by 2. Okay. So, if that has to happen, sigma 2 must reduce by the same amount, that means we are actually moving along this line. Okay. So, at point D, sigma 1 is equal to sigma z is equal to sigma y and there is no internal pressure, that means it is yielding under pure compression. Okay. So, that means I tried to explain using a simple cylinder how the state of stress lie on this hexagon. Okay. Now, what is the interpretation of this maximum shear stress theory for general 3-dimensional state of stress? So, this maximum shear stress theory represent a hexagonal prism in the sigma 1, sigma 2, sigma 3 principal stress space or the Hay-Westergaard space, where the axis of the cylinder coincides with the hydrostatic axis, or it is the space diagonal. Okay. That means, if you recall from the previous lecture, at any point on the hydrostatic axis, sigma 1 equal to sigma 2 equal to sigma 3, right. And we have just now proved that the hydrostatic state of stress does not affect yielding according to Tresca's criteria. Hence, it is a prism. You move along this axis, right, it remains a hexagon. Okay. So, hence this is a hexagonal prism where the axis of the prism is the hydrostatic axis. And recall that a plane perpendicular to the hydrostatic axis is called the deviatoric plane, and the deviatoric plane that is passing through the origin is called the pi plane. Okay. If I look at the cylinder from this direction, from the hydrostatic axis, what I get? I get this hexagon. Okay. And this is my sigma 1, sigma 2, sigma 3, 3 principal stress axis. Okay. Then I get this hexagon. I have tried to write the equations. For example, I will explain one. So, this line, the equation of this line is sigma 1 minus sigma 2 equal to sigma y. Why? Because if you go along this line, sigma 3 is changing, but there is no change in the yield condition. So, that means sigma 3 must be the intermediate principal stress. So, this is sigma 1 minus sigma 2 is equal to sigma y, or alternatively what is this point? This is sigma y. So, if you set sigma 2 is equal to 0, sigma 1 is equal to sigma y. Here at this point, what is sigma 2? Sigma 2 is minus sigma y. So, if you set this 0, sigma 2 is equal to minus sigma y, and this is the condition that I stated. In this case, sigma 1 is greater than equal to sigma 3 is greater than equal to sigma 2. So, sigma 3 being the intermediate principal stress. On the other hand, for this case, sigma 2 is the intermediate principal stress, and so on. Okay? This is called the Tresca hexagon on the deviatory plane. Okay? So, maximum shear stress theory is simple, or the Tresca criterion is simple, but as we discussed, it does not reflect the influence of the intermediate principal stress. You remember the cylinder problem, when we are increasing the internal pressure, one of the principal stress, which was the intermediate, was changing, but did not affect the yielding, right. So, this is one of the limitation of this, and it involves discontinuities. As you can see, it is hexagon. Okay. In plasticity theory, we will have to take derivative of the yield function, okay. Differentiate the yield function. Now, if you have this kind of discontinuities, you cannot do that. It is not very convenient for computational purpose. So, therefore, we will consider another theory which is called the octahedral shearing stress or maximum distortion energy theory, also called the von Mises theory, which is a convenient alternative. Okay. So, with that, let us summarize what we have done in this lecture. So, in this lecture, we discussed the initial yield criteria, or the criteria. We have discussed only one criterion in this case. Okay. How do we know a material under general state of stress is going to yield? Okay. So, we looked at the maximum shear stress theory, or also called the Tresca criterion, right. Now, in the next lecture, what we will do, we will look at the maximum distortion energy or von Mises criterion. Okay. So, with that, these are some of the references. I mean, the two references that I have used here: Plasticity for Structural Engineers by Chen and Han, and the Engineering Mechanics of Solids by Popov. Okay. You can go ahead and read more about this. Okay. So, with that, thank you and see you in the next lecture.